Hello everybody, Blake here. So today I kind of just want to show off a little collection of shaders that I've been working on. They're basically I've been working on this little side project called Raymarching, which is a rendering technique that doesn't utilize polygons very much. I mean, technically it still uses it. So like if I take this default material right here, you see that this is actually a cube that was rendering that sine wave that you saw. Uh, and so I'm not going to go too in depth into what exactly Raymarching is because there's plenty of good videos for that. But yeah, so I've just been for fun deriving some science distance functions, and let me tell you, some of them are bad. If if you've ever tried to derive a sine distance function for some shapes it's simple. For like circles, that's really nice. Paraboloids, not so much, but it's better than this. Yeah. Let's see. So this is the sine wave, and I can actually make it travel. I have the I have the line of code that causes that multiplied by 0, so it doesn't do anything right now. But f mod what 2 point that. So that's the actual distance function for it, which I mean, not a whole lot of. I can't imagine that a whole lot of people see or want to see on YouTube. I mean, I would like to start uploading this stuff to GitHub, so there might be a link down in the description at some point, but no promises. Uh, yeah, so I can make it travel, and I have a couple other shaders as well. I mentioned a paraboloid, so if I go and replace it with that, it's a lot less exciting. It's just like a nice little paraboloid. Uh, there we have it. I also have hyperboloids of single sheets, hyperboloids of two sheets, and then I just have this little thing which is a box with a hyperboloid cut out through it. So this is one of the advantages of Raymarching. You can do weird intersection and uh, smoothing operations between two distance functions, and it doesn't require anything too computationally expensive past, actually rendering them in the first place. But uh, so if we go back to the traveling wave, I kind of like to talk about a little. Oh, that's not the right button. I would kind of like to talk about how I did this a little bit. So go ahead and save that, and we got that there. So if I take a screenshot, I need a better screenshot than that. I need one that's kind of like down here. So let's say this is like the start of the wave. I'm just gonna do it in 2 dimensions since drawing in 3 dimensions is a little hard when I'm outside of VR. But and it's kind of harder to think about when you're not in VR, which most people on YouTube are not in VR. But anyways, let's change this to black actually. So here we have the sine wave, and oh, that definitely needs to be red. Never mind. So here we have the sine wave, and I'm just going to trace out like the first interval of like pi there, and then this would be like the interval from 0 or from minus pi to 0, and it'd be like roughly there. So we have the x-axis right here, and we have the y-axis right there. So actually, it might have been better to start with the paraboloid. Let's go ahead and do that. Let's see. Actually, yeah. So the paraboloid is probably the easiest example. This was the first one of these that I derived using this method. So again, in 2 dimensions, basically what I did is I solved the problem in 2 dimensions, and then I just translated into polar coordinates so that it is a surface of rotation. For those of you who have taken like second year or second semester calculus. So there we go. Go ahead and define our x-axis, and let's go ahead and define our y-axis. So we have the paraboloid right here, and so if you've taken vector calculus, you'll probably know that one way to optimize for the distance to a curve is to use Lagrange multipliers. We don't want to do that because that actually gives us a cubic equation, which is not very fun to deal with. Uh, but if you have a little bit more experience with Raymarching, you know that you don't actually need the distance function. You need just a distance underestimate. So what I do is I take some incoming point, like right here. So say this is where the camera is, and for every iteration, let's draw the rest of this in blue pen. I trace straight up or straight down to find the intersection of this, which is fairly simple. I just use this as the x. I use this one's x coordinate, and then I just evaluate the function at x. And I use a little bit of calculus to calculate the slope of this line right here. I put it into point slope form, find the normal line to it, so with the line that's perpendicular to it, and use point slope form to find that line here, and then just use a little bit of algebra from there on out to calculate this intersection point. And you can see this has a little bit of error to it, but once I do that again, it's going to be a lot closer, and then after another iteration or so, it's going to be pretty much right there. That one converges pretty quickly. In other cases, it doesn't converge quite so quickly. But there's a bigger problem with this method. So that's one that I refer to as a tangent method because, I'm using the tangent line. But the problem is it's only an underestimate if you're on the outside of this parabola. And for a sine distance function, in order to have all those fancy like intersection things, like you saw how I cut out the hyperbola from a box earlier, you have to be able to do it from both sides, which is the signed part in the sine distance function. So it requires a little bit more thinking to try to figure out a good way to do it inside of a curve. And the method that I ended up coming up with for the parabola specifically is that the normal vector down here is straight up, and then the normal vector over here asymptotically approaches straight horizontal. So logic dictates as long as this curvature doesn't change, it's probably not the correct mathematical term, but as long as this curvature doesn't change, i.e. there are no inflection points, which again, calculus, if there are no inflection points, then the normal vector along this is going to be between straight up and straight this way. So that means the normal vector here, the maximum value it could range from like here, and then it's going to go straight up. So if I go here, and this is all working under the assumption that the minimum distance to this point is going to be along a normal vector, which so far seems to be true. Note that how I don't say the normal vector, because in cases like right down here, there would be two normal vectors that would satisfy that case. And once you start dealing with other asymmetries and inflection points, it really doesn't generalize too well. But so we have so the maximum, basically this point right here, and then we do the same thing down for the maximum allowed, like just straight up vector. And we do that, and the rest I should switch to blue because that's probably going to get confusing. So now we take these 2 points, and we take this chord. So now, if you recall before, we took like a tangent line, red pen, and we crossed like that, and then we said, okay, so let's just find the minimum distance to this tangent line. And that's always going to be along this perpendicular line. And that one I know for sure. With lines, that's definitely true. Well, recall that the normal vector of this line has to be between this vector and this vector, which means the minimum distance can't be along any like line out here. So this is always going to give us an underestimate. So we just do this repeatedly, and then eventually it converges, which is how I initially derived the hyperboloid one. Because if I just erase all this stuff and use the parabola as a drawing board, if I draw a hyperbola of a single sheet, you'll see that the outside is actually the point where we have to use the chord method, and the inside is where the tangent method works better. Little y and x. All right, so let's go ahead and take another look at that sine wave, shall we? Marcher 2, sine wave. So now, it doesn't matter which one of these I choose really, but so now if I take, yeah, so let's take the 0 point like right somewhere over here. So if I take a snapshot of this so that I can draw on it, let's see, so we've got a red pen, and let's go ahead and trace across this. So this is the interval from like 0 to pi on 2 to pi to 3 pi on 2 to 2 pi. And wow, that was really terribly traced. But all right, so here we're kind of faced with a couple more problems. So initially you might, in this section right here, the tangent method works perfectly fine. In fact, I want to draw a little bit more out here just for demonstration purposes. The tangent method works fine. But the second you cross this line right here, you're going to run into some problems with the uh, original method. Um, anything past here, basically what happens is anything past here, if you go straight down, you'll see that this will actually give you an overestimate if in cases where like they were a point right here and then the normal would be along this way. I should have done that in a different color, but can I undo? Nope. Edit, no, okay, let's just try to erase all those individually. So that will give you an overestimate of the minimum distance, which means you overstep and the function doesn't work, and this SDF doesn't work. Uh, so the second you cross this line, you have to take a couple more things into consideration. You might also see that with the paraboloid, the minimum was straight up, but the minimum here is straight out this way. But it turns out it's kind of tricky to find the intersection of these two, this line and then that normal vector for any given point. So what I end up doing is at this point I call it the clamped tangent method, which is where instead of using the tangent straight down, I just use the tangent, and then the second I get past here, I clamp it so that the tangent is, the maximum tangent over here is along this line. Let me go ahead and draw that in. Blue pen. There we go. So this would be the tangent that I use for any point in this area, except now we're faced with yet another problem because once we get below a certain point, we also have to use the chord method. So let's see. So if I draw this little dotted line right here, um, obviously, obviously this isn't a formal math presentation, but so basically what happens is anytime we're below this line, the minimum distance to the clamped tangent is actually going to be an overestimate. So here is where we want to start using the chord method. So in the previous one with the parabola, you notice that I kind of skipped over this, but if I go straight down, that would be the same as taking this x coordinate and evaluating on x. And if I go straight across, that's actually the same as taking the square root of this height and then are evaluating the inverse function at the y coordinate of this point. So basically right here I would use the arc sine of sine and then to find this point, and then I would find you just evaluate the sine of the x coordinate to find this point. Except arcsine has limited domain, so there's a little bit more that you have to worry about. Basically, what I start doing is I drew the wrong section. I just realized. No, wait, no. So this wasn't important. So, or okay. So what I was just stuttering about is this is the y-axis. I forgot to draw that in, but it's not really important. So, and until now at least. So what I do in this case, to evaluate the arcsine function, I just take advantage of some of the symmetry, and then we got this little area right here. So basically, if I'm in this area, I flip it, move it over this way, and then if I'm still on this half, I'll flip that across this line, so that we're only dealing with this section right here. And so now we can successfully use the arctangent, and this little line over here becomes that line right here. So this is the region where we want to use the chord technique. Except again, just like with the tangent technique, you have to clamp some things because if we take the arc sine of here, we're going to get a point way over here, which I don't think I need to explain to you why that would be an overestimate. You can kind of visually see that. So we clamp the chord to be like right here at the minimum. So it's always going to be, so like if I was right here, we would trace this way and then evaluate the sine of this x coordinate, and then take the blue pen and that's our chord. So yeah, and that method is that's how I'm rendering everything. And my ultimate goal would be to make like a Raymarched graphing calculator, but that is pretty far away because this utilizes some really useful symmetry. But once you start getting into more complicated shapes with inflection points and overlapping functions that aren't like one-to-one, which basically they fail the horizontal line test, the inverse functions are going to get a little bit more complicated. They're going to have multiple solutions. I would have to probably pick the closest one, which would reasonably be not too bad. But yeah, there's a lot to take into account for at some point like that. But yeah, hope anyone that wanted to see that is enjoyed. I don't. Oh, I have one more little cool shader. This is all of the. This is all of my conic sections that I've remarched no, not. I don't want to look at the documentation, Unity. Thank you. I appreciate the help, but I got this. This one right here. Yeah. So this is actually this was inspired by my good friend Yuma, who he gave me the idea to Raymarch one SDF, and then once I was out of or once I got a hit there, I'd use the remaining iterations to march another SDF, and then obviously I did it again. You can see the hyperboloid's the first one, and then I got a cube here, and then the third one is all those really tightly packed spheres. And I just think this made for a cool shader. But yes, hope you enjoyed uh, that little mathy segment. But that's what I've been working on now that I finally got the water tutorial out. Hope to see you again.